Welcome everybody to this session. Jayasree's going to make a start and then we'll let it roll from there.
So, hello everyone. Firstly, I'd like to thank DVCon conference for providing me with this opportunity to present my paper. I'm Jayasree, working as an RTL design engineer in Qualcomm India Private Limited. And the title of my paper is Machine Learning for Coverage Analysis in Design Verification. So let me go over the agenda of the presentation. First, I'll give an introduction, followed by the problem statement, after which I'll go over the prototype implementation and the results of the same, followed by the applications, and finally the conclusion. So I'll start presenting my paper. Coming to the introduction, coverage analysis is a key aspect of RTL verification for measuring the accuracy of the testing of the design. The main aim of my paper is to develop an algorithm that will automate and speed up the coverage closure process with the help of machine learning techniques. From the algorithm, the set of essential and redundant test cases from coverage perspective can be identified. This is done by the selection of optimal combination of features that will maximize the coverage percentage in minimal runtime. Moving on to the problem statement, coverage closure is usually carried out towards the fag end of the projects. The coverage database, which is generated by the VCS or any other similar tool, is manually analyzed by the engineers for different types of coverage, such as line, conditional, branch, or episoden. This process involves large amounts of data and is having lots of randomness in it. Because of this, there is a possibility of higher CPU resources being consumed when test cases are run unnecessarily. Moreover, this process is also very time consuming and involves a significant amount of manual effort. So, in order to address these problems, the algorithm presented in the paper aims at intelligent selection and elimination of test cases with the help of machine learning. It also aims at smarter selection of constraints while running regressions by reducing the randomness in them. The figure here gives an overview of the stage of the coverage closure process wherein the algorithm will be inserted. In the existing flow, the coverage database, which is generated for a large set of test cases, is manually analyzed by the engineers, based on which the sequences are modified and regressions are rerun to cover the uncovered scenarios. In the proposed solution, the coverage database, which is generated for an initial basic set of test cases, is analyzed with the algorithm and machine learning techniques, based on which the sequences are modified and the regressions are rerun. Moving on to the prototype implementation and results section, a prototype of the algorithm has been developed using the RTL code and the regression results of a module having a complexity of around 3 lakh NAND2 gates in 14 nanometer technology. The implementation is a 3-stage process. The first stage involves the prediction of the coverage percentages and simulation times with the help of machine learning models. The relationship between the inputs and outputs of the model is non-linear. So I've experimented with decision tree and random forest models in the prototype. Coming to the inputs and outputs of the model, the features of the model are parameters which are fed as input arguments to test cases, based on which the functionality and the section of the RTL code that is covered will vary. These parameters are fed as Bernoulli distribution to the model, which means if a particular feature is present, it will be indicated as 1, and if it is absent, it will be indicated as 0 in the model. For instance, if encryption is a feature that can either be enabled or disabled in different use cases of a product, if it is enabled, it will be indicated as 1, and if it is disabled, it will be indicated as 0. The labels of the model are the coverage percentage and simulation time of each test case. The training data set is a set of basic test cases whose coverage percentage and simulation time are known. The test data set is a set of test cases with a combination of features whose coverage percentage and simulation time are unknown. The outputs of the ML model are the predicted values of coverage percentage and simulation time for the test data set. The figure here gives a pictorial representation of the inputs and outputs of the ML model. Once the model is trained and validated with a known dataset, it can be used to predict the unknown values of coverage percentage and simulation time for the test dataset. The table 1 here shows the inputs that are fed to the ML model. Each row of this table represents a test case, and each column represents a feature for columns 2 to 9. The value 1 in the cell of a row indicates that the corresponding feature is present in the test case, and the value 0 in the cell of a row indicates that the corresponding feature is absent in the test case. For example, in the first row, that is the first test case, features 1 to 6 are present, but features 7 and 8 are absent. The last two columns represent the actual values of coverage percentage and simulation time used for validating the model. The table 2 here shows the predicted values of coverage percentage and simulation time using decision tree and random forest models indicated as DT and RF respectively. From the table, we can see that the actual and the predicted values lie very close to each other, especially for the decision tree model. The table 3 here shows the predicted values of coverage percentages of different types of coverage such as line, conditional, branch, and finite state machine. Here, decision tree model values are shown since it has better accuracy. The figures here provide a graphical representation of the actual and the predicted outputs of the ML model. In both the figures, the x-axis represents the test case. In figure 3, the y-axis represents the coverage percentage, and in figure 4, the y-axis represents the simulation time. The line in blue indicates the actual value of coverage percentage and simulation time, and the lines in orange and gray represent the predicted values of coverage percentage and simulation time using random forest and decision tree models respectively. Here as well, we can see that the actual and the predicted values lie very close to each other. So with that, the stage 1 of the algorithm is complete. Coming to the second stage of the algorithm, this stage involves the computation of a parameter called score. Score is computed as a linear combination of the outputs of the ML model, that is the coverage percentages and the simulation times. There are two methods by which score can be computed. In the first method, score is computed as a function of the overall coverage percentage and simulation time. Here, score is alpha into coverage percentage minus beta into simulation time. Simulation time is subtracted in the equation since it impacts the coverage negatively. In the second method, score is computed as a function of the coverage percentages of different types of coverage. Here, score is alpha into branch coverage plus beta into conditional coverage plus gamma into FSM coverage plus delta into line coverage. All four values are added in this equation since they all impact the coverage positively. Alpha, beta, gamma, and delta are scalars that can be selected and tuned by the verification engineers based on the priority of the outputs and the project requirements. For example, in the first method, if the reduction of simulation time is having higher priority in a particular project, then the scalar beta can be assigned a relatively higher value. Similarly, in the second method, if line coverage is having higher priority or covers a larger section of the code base, then the scalar delta can be assigned a higher value in the computation of the score. Higher value of score indicates better coverage in lesser runtime for a test case with a given combination of features. The tables here show the computed scores as a function of the overall coverage percentage and simulation time, that is method 1, and as a function of the coverage percentages of different types of coverage, that is method 2, for certain values of alpha, beta, gamma, and delta. In both the tables, each row represents a test case. From the table, we can see that the first test case is having the maximum score, and the last two test cases are having the minimum scores in both the methods. Now, this is a very intuitive picture because in the first test case, more number of features are enabled, hence a larger section of the code base will be covered by it. In the last two test cases, lesser number of features are enabled, hence only a smaller section of the code base will be covered by them. Moreover, in the first table, implementing the first method, the scalar beta is having very less value in the computation of the score, which means simulation time is having very less value, very less weight in the score computation. In the second method, the computation of score is independent of the simulation time, and it only depends on the coverage percentages of different types of coverage. So, the higher value of score can directly be correlated to more number of features being enabled in the prototype. So, with this, the stage 2 of the algorithm comes to an end. The third stage of the algorithm involves the computation of the relative impact of each feature on the coverage percentage and the simulation time. For the coverage percentage, for the given set of test cases, we first compute the mean coverage percentage. Then, from the given set, we take the subset of test cases that include the feature. And for each test in the subset, we compute the difference between the coverage percentage and the mean coverage percentage. The mean of all these values will provide the coverage increase with the feature. Similarly, we take the subset of test cases that do not include the feature, and for each test in the subset, we compute the difference between the coverage percentage and the mean coverage percentage, and the mean of all these values provides the coverage increase without the feature. The impact of the feature on coverage can be computed as the difference between the coverage increase with the feature and the coverage increase without the feature. Similarly, for simulation or runtime, we first compute the mean runtime, then we compute the runtime increase with and without the feature, and the impact of the feature on runtime can be computed as the difference between the runtime increase with the feature and the runtime increase without the feature. The overall impact of the feature can be computed as alpha into coverage impact minus beta into runtime impact. Here as well, the runtime impact is subtracted in the equation since it impacts the coverage negatively. The figure on the right shows the relative impact of each feature on the coverage percentage and simulation time. The x-axis represents the feature and the y-axis represents the relative impact. From the figure, we can see that features 1 to 5 are having the maximal impact on coverage, and features 6, 7, and 8 are having the minimal impact on coverage. Coming to the productivity improvement, in the previous slide, it was inferred that features 6, 7, and 8 are having the minimal impact on coverage. Hence, it is sufficient if we run fewer sets of test cases with these features enabled. For example, before the implementation of the algorithm, if 20 sets of test cases were run with these features enabled, then after analysis through the algorithm, it is sufficient if we run 5 sets of test cases with these features. The CPU time that is saved can be computed as the product of the number of sets of test cases that are not run with these features and the simulation time increase due to each of these features. The percentage savings can be computed by dividing the CPU time that is saved by the total time taken to run all the sets of the test cases. In the prototype, for the given set of test cases, around 2400 seconds or 25% of the CPU time can be potentially saved. The figure on the left shows the simulation time increase due to each feature, which was computed using the formula shown in the slide explaining the relative impact. The x-axis represents the feature and the y-axis represents the simulation time increase. From the figure, we can see that feature 4 has the maximum runtime increase and feature 2 has the minimum runtime increase. And the figure on the right shows the CPU time that is saved with the help of the algorithm. The x-axis represents the seed number of the test case, and the y-axis represents the aggregate runtime that keeps increasing with each seed. From the graph, we can see that up to seed 5, the runtime remains the same with and without the algorithm. Seed 6 onwards, there is a gradual reduction in the runtime of test cases with the algorithm. This is because from seed 6, features 6, 7, and 8 are disabled in the test cases. So there is a reduction in the runtime of each seed and an overall reduction in the aggregate runtime as well. Coming to the applications, the key advantage of using this algorithm is the reduction in CPU time and human effort while performing sanity testing on modules having a large code base. Tests that are redundant from coverage perspective can be identified and unnecessary reseed runs of the same can be prevented. Moreover, from the algorithm, the RTL engineer can have a better understanding of the functionality of the input arguments to the test cases and their correlation with the RTL code. Through this, there can be a reduction in the randomness of constraint selection in modern verification techniques. Coming to the conclusion, the algorithm presented in the paper is a prototype that demonstrates the application of machine learning in coverage analysis. Using the algorithm, the impact of any new feature on the coverage numbers and its correlation with the existing features can be understood. In this paper, code coverage has been the key area of focus. Further, a model can also be developed that will combine the database of both code and functional coverage and provide an optimal combination of test cases and features that will maximize the coverage. So, it can be concluded that there is a huge scope for machine learning in improving the efficiency of coverage analysis in verification. So with that, I've come to the end of my presentation. Thank you very much for your time and patience. Please feel free to ask me any questions.
Really brilliant presentation. Thank you very much indeed. Are there any questions? I don't see any on the chat. So, oh yes, there are some coming through now. Are you, Jayasree, are you able to see the?
Yeah, I can see the chat. Yeah.
Yeah. Do you want to go right ahead and answer some of the questions?
Yeah, the first question in the prototype, it was a small set of test cases inside 30 to 40 tests only. But in the actual implementation of it, we can include even a larger set of test cases in reality, which will cross over 500 to 1,000 test cases, especially for the larger modules. Coming to the second question, how many features did you have? So in the prototype, I took 8 features for the testing. How should non-binary, coming to the third question, how should non-binary constraints such as delay in clock cycles be used as an input in the neural network? So for non-binary constraints, if it's a discrete variable, we can still go ahead and continue with the same model for predicting the values of the coverage percentages. However, if it is a continuous variable, I think the complexity of the model may increase. Coming to the fourth question, how large was the neural network number of nodes? I'm not quite sure of this question actually. So,
how large is it?
I have.
Hi, can you hear me?
Yeah, I can hear you.
Hi, thank you for answering the first three questions. For the fourth one, I wanted to know when you define the neural network, how many nodes did you use? I don't know, do you define, for example, like it's in TensorFlow, you define a number of nodes and all this on each layer of the neural network? Did you use TensorFlow or did you build
no,
your own?
I just used basic decision tree and random forest models. And
Okay.
and further, I built the algorithm computations on my own.
Okay, and I don't know anything about these decision trees, but I'm imagining like there are like nodes, and each node has some weight to use for the next one. How many
Yes.
of these nodes did you have in this decision tree?
The nodes were actually what I did was I used the built-in package in Python for the decision tree model, and I think around 4 nodes were present.
Okay, thank you.
I suspect that there would probably be other questions. I very much encourage, almost demand, that everybody on the chat, as soon as this session ends, that we go to the virtual room, and I would hope that we could even say that we'll all meet in the blue room, where the big ball, earth ball is, if you like, and the speakers can come there and we can ask more privately, if you will, or at least in a more easy setting, questions that you don't want to ask here. There are a couple more questions coming in, I think. One more question from Sumit.
Yeah. How did you verify the machine learning models or algorithm? Is there a software testing in place to test if the ML is working fine? So as of now, there is no software testing available to verify if the model is working fine. But we can definitely create one to ensure that the model is working fine. The initial implementation of it may be somewhat complex, but once the model is in place, we can keep reusing it across projects.
Okay, in which case, if there are no more questions, it'll be good if we have some extra time at the end to go into the virtual world and to continue the chat, because I think there's some very interesting points being made. So let's, yes, absolutely, Christian. I think that was an excellent presentation, and I think we should do a round of applause if we can.
Thank you.
Albeit virtual. Let's move on to the next presenter, who is Hachem. Hachem?
Hi, everyone. Yeah,
Hi, I'm not quite sure how to...
Yeah, it's Hachem. Hachem, yeah. Thank you for the presentation. That was really interesting. Let me share my screen.
Sure, go right ahead.
Everyone can see?
Looking perfect.
Excellent. So yeah, thank you really for attending this presentation. I will be presenting our paper SimPy for chips, where I will explain how we build a discrete event simulation framework using only Python. And the purpose is to model large-scale machine intelligence accelerators. But to give a bit of context about why this work, let me tell you a bit about what we are trying to do at Graphcore. Our goal really is to efficiently accelerate machine learning workloads, and these are becoming really huge. And as this happens, really a single chip that fits the whole model will not be enough. So what we do is we design a single reticle limited chip that we call Colossus here on the left, and then we put this chip here will have a core of many tiles, and then it has a system on chip that allows it to communicate with the outside world, whether it's a host or other similar chips like this to cooperate the workload. And then we put 4 of them in a box, and then 16 boxes in a rack, and then connect up to 64 of these racks together, and you have a total of 4,000 chips. These could be working on a single program, a single model. And basically in system architecture at Graphcore, we are always thinking about this 4,000 chips working together when we are designing for this single chip. So this is a bit to motivate why we did this work. Moving on to the agenda, I will talk briefly on what is the state of the art in the architectural validation space. And then I will explain the motivation behind this work. And then I will dive into the SimPy package and what it can offer. Then I will discuss how we extended this package to overcome some limitations of native SimPy. Then I will introduce our modeling framework to organize very large systems into a hierarchy and provide the interface between them. Then I will briefly talk about our library of generic components that we are making available and open source. And this will help us to build powerful systems. Finally, I will conclude with some future directions. So mistakes and iteration in the specification stage are cheap to correct, much more expensive in later stages. This makes really the exploration and validation an essential step where the design gets refined. Now, this modeling typically is done using System C, C, or C++, which is not ideal for productivity, but recently we have new libraries that are actually trying to close this productivity gap. And we've seen yesterday in the tutorials as well some Python and System C combination that is trying to do this. Also, the tools that we find are often concerned with cycle and resistor transfer levels and sometimes functional as well on a single chip, rather than looking beyond a single chip on how the whole system will operate. And finally, they are not, as I just said, they are not concerned with this bigger picture where the application requirements are being met by this design when you put multiple chips together. So we are always thinking about, as I said in the beginning, we are always thinking about how we can make a single chip work. We make a single chip that will work perfectly with many more of its sister chips, really. And then that's towards the goal of accelerating machine learning workload. And we want to be able to peek on how this large system can behave and can function, and whether it meets the application requirements before we actually start writing the RTL for the single chip. And even after the chip comes back, we want to have a framework that allows us to explore the space of its configuration, not only so its register configuration, routing, and stuff like that. We want to be able to explore new topologies, multi-chip topologies, basically, and we want to debug in-field problems, which I will come to this later. Now, the available tools place big importance on the vertical mobility between functional and cycle and register transfer levels. So we want things to be transparent across these and mappable between these levels, which means they have to maintain a fair bit of details in terms of the accuracy, in terms of avoiding more abstractions. And this makes the simulation of scale-out systems like the ones we're interested in very slow, and hence it limits how much exploration we can do. So this motivated us to work around this and come up with something. And the first step was to look at the SimPy package. It's a Python package that offers really abstract classes to build discrete event-driven simulations. These include an event class, a process class, and then an environment class where all the events and processes live, and they get handled by this environment according to a schedule. On top of these abstract classes, it provides also concrete components such as stores, resources. These can really be used and modified to simulate a system of queues and a system of storages. Now, as the simulation runs, events and processes will create a kind of like a chain reaction between them, where an event getting triggered will trigger another event, and so on. And these events are added to a Python heap structure, each with a time step on when it will happen. And then these gets processed in increasing time. Now, at the same time, the environment would be popping things. So some processes will be adding events to the heap, others, and then the environment will be popping out from the heap and processing the events at the exact time where they should be processed. And basically, that's how the concept of time is created. You can find similarities with how System C works, except that mostly in System C, you care about cycle by cycle, whereas here you just, the notion of time is explicit. So basically this event will happen, I don't know, at time X, and then that's when it's scheduled. So you can imagine how you would move through the list of events much faster, where you don't have a tick where nothing happens, basically. Now, processes are based on the native Python generator function, and utilizing the yield statement, which is native to Python, to block the execution until some event or another process successfully occurs before resuming the execution of the program. Now, this event-based rather than cycle-by-cycle approach is highly suitable for complex systems with many components, and where we need more and more abstraction levels to run faster simulations. To give you an example, here we have an example that shows how we can easily construct a pipeline object and with its depth configurable. The input here is a capacity 1 SimPy store that holds whatever is sent down the pipeline. Here you can see it, and then the run method basically does the actual processing, which is to get this item from the store and run a latency process. Now, the latency process here will wait for the time to traverse the pipeline before putting the item in the downstream, simulating basically what a pipeline does. Note that in the run method, a process is added to the environment. So here we are adding to the environment a latency process. This is not blocking, which means that as soon as this is added to the environment, you don't wait the time. You just move back here and then do the next item, send the next item down the pipeline. Which is basically what a pipeline does, right? And this can be customized such that the latency process is not only a wait time, but you can have any kind of processing, like compute happening here. The key is that the compute can start on new items before it has finished on the other items. And to see it in action, here's a test bench, a very simple one again. You have a pipeline and then a downstream store where things get received. And as a stimulus, we have two processes: a send process and a retrieval process. A send process will basically send 10 integers numbered 0 to 9 down the pipeline. And in between them, it waits a number equal to the a number of cycles equal to the integer incremented by 1. So basically, you send 0 and then you wait 1 tick. You send 1 and you wait 2 ticks, and so on. And then the retrieval process will simply get something from the downstream and then print out that it successfully retrieved it from the downstream. And basically, the result will be something like this. So the @ here is the cycle ID or the cycle, the tick, which tick this has happened. You can see that what I explained before about what is this supposed to doing is actually happening. You have the first integer is sent at 0, then the other one is sent at 1, and then you wait 2 ticks before sending 3, then you wait 3 ticks before sending sorry, you send 2 and then you wait 3 ticks before sending 3, and then you send 3 and you wait 4 ticks before sending 4, and then only after. And by the way, in this case, the depth of the pipeline is 6, so you can expect 6 ticks between the start of sending and the retrieval, which is exactly what's happening here. You can see that this is where you send the first integer, and this is when you receive it at 6, and then the second one as well at 1 and 7, and so on. So this is all good, but imagine an operation that takes a known number of cycles after which an event actually happens, and this event in turn will trigger another event to happen, and so on. Now, knowing when this event would happen and scheduling it at that point is important, and it's very common in simulating ship processes. So say, for example, you have a fixed delay to open a memory row, after which you can read that memory row. SimPy doesn't allow this, natively doesn't allow events to be scheduled at a future time, except for a single event called a timeout event. This is quite similar to the wait function in System C, but here you can actually, for the timeout in SimPy, you can actually specify how long you want to wait before this event is triggered. So in order to simulate, in our case, in order to simulate when something other than a timeout takes a fixed number of cycles, we initially resorted to using a lot of explicit timeouts, followed by the actual event of interest being triggered. This hurts the performance, and it goes against really the event-driven simulation, and we are rather setting explicit times instead of just events triggering other events. Now, to allow us to build these performant and scalable models that I've spoken about before, we actually extended the SimPy's event class and created something called a new event class that allows for exactly what I just said. Using this, we can directly schedule events such as the end of writing of X bytes to memory will happen at this time, which in turn unblocks further queued writes, and so on. Now, this new event, we use it really everywhere in our framework as the base class for many of our custom-made events for using buffers, pipelines, arbiters, etc. Another limitation, so you can see here a simple implementation of a buffer using standard SimPy. The difference between a store, which is existing already in a SimPy, and a buffer is the concept of time, where writing is not instantaneous to a buffer. It might take some time to write into a buffer, whereas a store, you can just immediately store something into it. So you can see that the put method here contains 2 elements. The first one is a timeout. So you wait for a put delay, the time it takes to put the item, and then you actually put it in the store, and then you block until that. So now, since you've used a yield statement, it is a generator function, this put, and hence it is a process in the terms of SimPy. It's not an event, which means when you want to add it, when you want to actually put something, you need to call env.process buffer.put item rather than just the more intuitive and desirable API where you just say buffer.put item. This is not possible using native SimPy. You have to extend the core components of SimPy, and this is what we've done. And this really makes the API much more intuitive. So what we did is that we actually went into the trouble of changing internal SimPy elements such that some of its methods, internal methods like the doGet and the doPut methods of the SimPy resource class, in order to embed in it some timing features and to support complex events. For example, our buffer component has a comprehensive timing features like the time before read and write can proceed, the time needed for the read and write to actually complete. And yet all these features are really buried, and they are not exposed to the user other than just the parameters that they can decide and set. But their API call is simply as here, buffer.put item, and the backend will take care of everything. Now, we've built a modeling framework of how we actually structure a system or a model or a chip, whatever you want to build with it. And here I'm showing a schematic of the hierarchy that we implemented. And then we have basically generic classes like a component, a unit, and a platform. A component is the smallest connectable entity. It is the smallest thing that can be connected to other things. A unit extends a component to contain a collection of connected components and units. And finally, a platform really extends the unit with add-ons to actually add stimulus and monitors to the different ports of these units. Now, the interfaces between these classes are standardized using common handles implemented as Python dictionaries. You have the to downstream and to upstream, and the from downstream and from upstream. So these are 4 dictionaries. Now, the to downstream to upstream contains references from which the component can call API methods in the upstream or downstream components. And then from downstream and from upstream contain references from which upstream and downstream components can call API methods of this component. Also, we have a connect method, which is a general method that is used to connect independent units, but also the internal entities of a unit or platform while exporting top-level connections for prospective inter-unit connections. So you have basically, you can see here, you have a port of a subunit. So here's a subunit, and then a port of it is exported to be a port of the higher level unit. And then this connects to a port of the higher level unit, which is basically an exported port of the subunit of the other unit. So this is all handled directly by this connect method. You don't have to do it manually. You just connect. You just say you export the port here, and then you connect it to the port here, and then this connection of to downstream here to from up here will happen automatically. Now, in the open source library that we're making available, we've built some abstract classes and some actual components that can be used to build systems. The abstract classes we already discussed, which are the component, the unit, and platform, as well as the base component that contains really just the logging features. And then we have the base packet is an abstraction of a datum that can be sent between units. This could be really customized to be anything you want. For the actual components or blocks, we have built building blocks that are frequently used in chip design. These are a buffer in its different flavors, like flow control buffer, normal buffer, credit buffer, a store and forward buffer. The default buffer is basically a cut-through buffer. And then we have built also a pipeline and a flow control pipeline, a crossbar, which is a generalization of an arbiter with multiple inports and multiple outputs. And then we have a specific instance of this crossbar, which is a round-robin crossbar that implements on each output port a round-robin between the contending imports. These components are highly configurable, like the buffer capacity, the read and write delays, read bandwidth, pipeline depth, etc., to suit every different project and can be customized easily, which makes exploration much faster. Now here's an example we've built. We have 6 processors talking to each other through 6 routers, and this is the structure of the router here. You have a stream coming locally, and then a stream that is coming from the attached router, and in each direction really you have a ring of processors here. And basically you have an arbiter here that arbitrates between these 2 streams of traffic. and sends one of them here. This is a round-robin arbiter. And then you have the ports that are connected. You have 2 ports that are connected to the router, and then 2 ports to receive from the router for each processor. We can build this easily with the stimulus and everything and run a simulation using only about 200 codes of Python code, mostly comments as well. And in order to do that, you can go hierarchically. So we basically we have the following subcomponents that we build. We have the router, which uses flow control pipelines from the components I've discussed before, and then flow control buffers as well. We built a round-robin arbiter, again, which is just an instance of the round-robin arbiter that we have. A processor, which is basically, in this case, just a stimulus that generates packets and sends them, and then also a monitor that waits for expected packets. And then basically we have the platform in which we add the stimulus and stuff like that. So really it's very simple, and you can see the code in the repo, we have it there. Now just a note on why this was useful to us. So before we tape out our first chip, now these models enabled us to detect really and resolve many number of head-of-line blockings that were happening inside the chip, and we fixed them before we actually tape out the chip with these defects. Now, also, when we started to build this large system of multiple chips on Mark II, and we've added some visualization features that enabled us to really replicate deadlocks that were observed by external customers. Now, this is an interesting one because in verification, your test benches are always on a single chip. But what do you do when you have multiple chips and the deadlock, which means basically a cyclic buffer dependency between spans multiple chips? This was something that wasn't detected by verification simply because they verify the single chip, but it was caught by our simulator, and then we devised workaround through routing reconfiguration of the interconnect to avoid actually these dependency, and we successfully basically mitigated this in-field deadlock. Which I find really very useful to be able to do this very quickly. Also, we have been able to find and address non-intuitive instances of unfair arbitration. You have all kinds of unfair arbitration when you have rings, and this is what we have, and this will lead to I/O underutilization of the chip, basically. Also, when it comes to cooperating with the application and software, we have been able to simulate the performance of collective operations, which is very useful in machine learning workloads when you have multiple chips running the workload. And then we were able to reach an optimal utilization of I/O bandwidth, which is, again, very impressive, I feel. As a conclusion, really, our approach to exploration allows much faster validation when the target is a scale-out system and the application level of abstraction is needed. Our SimPy for Chips framework will provide an intuitive and easy-to-use API to build and simulate complex systems in a short time, and really it requires only Python. It doesn't require other maybe hard-to-find skills. Now, as a future work, we will continue to produce fundamental and improve fundamental components. We will add standardized debug features and also some visualization features to help debug real cases. And really, thank you. I'm Hachem Yassine, and these are my co-authors. And if you'd like to join us at Graphcore, we are always hiring. So if you have any questions, I'm happy to answer them. Thank you.
Thank you very much indeed. A really interesting talk and a really interesting use of Python as well. Are there any questions from the audience? I'll start off with one. You mentioned SysPy, I think it's called, or PySys, I can never remember which way around they call it, that has been recently made public through the Accelerator Common Practices Working Group, and is now available for download. That thing's kind of interesting too. Is there scope for combining the two together? Is there a good reason for doing that or not?
Yeah, that's definitely something I've thought about yesterday after the tutorial. And I think, yeah, we will have to take a look at it actually to see where it fits. And but yeah, it's definitely very interesting, and it shows that there is a momentum in that direction, really, in Pythonizing flows to make them really faster.
Absolutely. I think a lot of people are very keen on using Python, and yeah, it would be nice because it would give you a seamless way of integrating Python, System C, different parts together.
It gives you also the flexibility, whether you want a really very accurate model or you want a coarse model, and having the option is useful, where you can just have these toggles that you can enable and disable, and then suddenly your simulation will run faster or slower with different levels of accuracy. So that's really, yeah, very useful, I think.
Are there any other comments from the audience? Again, I hope that, well, no, I'm in, oh yes, hang on, there is one. We'll take that before I tell you all to go to the virtual rooms again.
Is there any support for converting an existing model written in C++ System C to Python instead of writing it from scratch? Unfortunately not, no. This is a really, because it started as a company-specific project, so but hopefully there will be scope in the future to extend it, and as we just said about the PySys, so yeah.
Again, I think this is a really interesting topic, and I hope you will enter into the virtual room. I'm going to suggest that we all meet in the blue side room, and I would hope that everybody in this group goes there, meets, and discusses with the three authors who are presenting this morning, or this afternoon for various of you, or this evening or early hours of morning. Speaking of which, Sandeep has joined. Sandeep, would you like to introduce yourself, and we'll move on to your presentation. And thank you very much indeed for your presentation, Hachem.
Thank you.
Fantastic.
Cheers.
Hey, Mark. Thank you. I guess good morning, good afternoon, and good evening. That covers all of
yes, and good night.
Good night, yeah. So I'm Sandeep Srinivasan. I'm the founder of a startup called Verifai. We're based in Palo Alto, California, and a distributed team. We have some folks in New York, some in Bangalore. And what we're trying to do is solve verification, hardware and software verification, by using machine learning and some advanced techniques in machine learning, such as reinforcement learning, and also language models such as BERT and GPT-3. So my background is, I started out my career many years ago at AMD in the microprocessor division. And since then, I've founded 4 startups. 2 of them have been in EDA, in the space of low power algorithms. And then 1 has been in the space of a mobile app that uses machine learning. And then the latest startup is Verifai. So I'm going to share my screen. So the topic of our paper today is called Optimizing Design Verification Using Machine Learning and Doing Better Than Random. So the primary authors for this paper are Bill Hughes, me, which is Sandeep Srinivasan, Rohit Suvarna, all 3 from Verifai, and Maithilee Kulkarni, who's with Xilinx, and Maithilee was also a intern at Verifai, and she's significantly contributed towards this paper and more while she was at UT Austin working with Jacob Abraham. So the agenda for today's talk is we'll sort of briefly touch over some of the design verification challenges as we see them. And we'll pick a code coverage example as a toy motivational example and demonstrate how we might do better than random. And then we'll talk about how we apply machine learning techniques for this code coverage example. And then apply the same machine learning techniques for design verification. And we'll talk about two real-life test cases. One is a messy cache controller design from opencores.org. And the other one is a RISC-V 64-bit design, which used to be called ARIAN, and recently they've changed the name to CDA6. I'll touch upon a little about the future direction and our vision of what we see of machine learning's part in design verification. And then we'll conclude with a few of our thoughts and findings. So verification complexity is growing rapidly, as you can all attest to. This is a slide from DARPA, which is by Andreas Olofsson, dated 2017. I think it's a visionary slide where essentially what he's showing is that the cost of verification is approaching or greater than 50% of the cost of the total design. So this is a pretty alarming slide. And specific to hardware verification, there's about 4 verification engineers per design engineer. And the verification costs about 55% of the entire design cost and are rising. In addition, hard bugs are found late in the project. So now if you look at the software side, there's about 1.5 verification engineers per developer, and security bugs are typically found in production. So this is a growing challenge in the software industry as well. So there has been significant innovation in verification, UVM methodology, formal verification, so on and so forth over the last 2 decades. And if we could broadly categorize them as to how people use it currently is, we use a lot of random tests. The efficacy of random tests are very low, but also the human effort in creating these random tests is low. Then we have constrained random, directed random, feedback random, and the effectiveness of finding bugs is sort of medium with this approach, and this is sort of a majority approach. And the human effort, I would say, is medium to high for these techniques. Now, obviously, directed tests give you the highest efficacy and effectiveness in finding a bug, but also it's the highest human effort. So the question we asked ourselves is, can we do better than random in humans in less time? So the answer is yes, but a new approach is required. So in order to explore this new approach of doing better than random and better than constrained random, we came up with this motivational example. And it's a toy example with 3 levels in a nested if condition. And the control flows to a lower level depth only if the values of ijk satisfy a particular range constraint. So for instance, I needs to be in the range of 1 to 26, and if j is in the range of 26 to 51, and if k is in the range of 51 to 76, we reach this line of code, which is depth of 3. Now, depth equal to 3 is just a proxy for a very hard to reach condition or state, right? So this could be in hardware, could be in software, could be in a state machine. So the question we asked ourselves is, can we train a neural network to learn to produce the best ijk values without exhaustive random combinations? And then the other question we asked ourselves was, how does random selection of IJK perform as compared to a neural network that we will build? So now, just to put this in context, is the total number of states in this toy example is just 6561. The total number of atoms in the universe is 2 to the 287, approximately. The total number of states in a Go game, which Google famously beat Lee Sedol, the Go champion of the world, with an AI machine called AlphaGo, is 2 to the 602. And the total number of states in even a small microprocessor can be 2 to the 2 million. So the complexity and the state we're dealing with for hardware verification is significantly large. So now I'm going to just dive into what we applied specifically for this code coverage problem. We used a reinforcement learning algorithm called Q-learning. And Q-learning essentially, the picture on the left shows the software agent that takes an action on an environment, and then the environment returns back two things. It returns back a reward, which is a scalar, and returns back a state. And based on this state and reward, the agent takes the next action. So the very simple formulation. And in Q-learning, the goal is to maximize what's called cumulative future reward, which is given by this equation called the Bellman's equation. So in this particular case, Q of pi denotes a particular policy or a set of distributions of reward and state and action that the reinforcement learning agent learns. And the formulation for the Bellman's equation is recursive in nature, where the state and action depends on the cumulative future reward, and our goal is to maximize the cumulative future reward. Now, the Q value is also called expected return, or the value of estimated cumulative future reward. You'll notice there's this factor gamma here, which is known as a discount factor. And the discount factor essentially discounts some of the future estimated reward, because we can never actually truly predict what a future reward might be. Right? So for more on this topic, the book by Richard Sutton and Bartow is fantastic, and I'd encourage all of you to look at that if you haven't already. So the core of a DQN are Q values, as I just mentioned, where Q represents the discounted future rewards for a particular action for a particular state. So now DQN is just a Q-learning algorithm that uses a deep neural network. And the reason we use a deep neural network is when the state becomes very large for a simple lookup table. So we use a DQN, which is a Q-learning algorithm with a deep neural network. So now we applied the DQN to the code coverage example that I just showed you. And the RL agent, without any prior knowledge, learns by trial and error that I should be in the range of 1 to 25, J should be in the range of 25 to 50, and K should be in the range of 50 to 75 in order to maximize the average code depth reached. So you can see the results here on the right, where the blue line indicates random choices for IJK values, and the y-axis represents the average code depth reached, right? And the red line shows the Verifai RL agent that very quickly learns, after 500 episodes, how to produce an average code depth of 1.8 and above, And after 2,000 episodes, it quickly learns how to consistently produce IJK values that lead to an average code depth of 2.5 and above. So there's another factor in reinforcement learning where you can trade off exploration versus exploitation. And this is denoted in this graph by epsilon. So if you set epsilon to 0, that means you're always exploiting. So in this particular graph, maybe it would have sort of plateaued out at 1.8. Now, when you set epsilon values slightly higher than 0, it goes into this mode of exploration where it periodically explores with random IJK values. And that's where you see a jump in the learning. So now we apply the same DQN for design verification. And the setup for DV, for design verification, is depicted by this diagram on the left, where you have a design under test, and then you've got an initial random knob settings for the device under test that then goes into a simulator, and the simulator output then goes back into the reinforcement learning agent, which produces the next set of knobs to feed back into the simulator. So you can think of it just like the knobs for the simulator are DV controls, design configuration, plus args. And just like I explained, it's as simple as choosing the IJK values. And we also pick an output or output metric to optimize. In the code coverage example, our goal was to optimize average code depth reached. But with design verification, our goal can be optimizing coverage, code coverage, function coverage, optimizing specific things like FIFO depths, victim buffer counts, that all depend on the knob settings. So the knobs need to be controllable and observable to make a difference to the output. So the DQN is modeled, or this problem is modeled as a MDP, Markov decision process, where it's a mathematical model for control systems where the current state is sufficient for the software agent to take an action. And then again, we use the deep Q network here, a DQN, to train an RL agent to learn a policy of Q values. And in addition, if you had prior simulation outputs that we had in this particular case, we use that as prior ground truth of what's called an experience buffer that the reinforcement learning agent can learn from. So the first test case, as I mentioned, was a messy cache controller design. So the cache controller design supports a quad-core CPU. And it's a 4-way set associative cache of size 256 KB, one for each CPU. It has a 4-bit offset, 12-bit index, and a 16-bit tag. And this design is available at opencores.org. And I'll also share, we've put this design up on our website for you to try this experiment live. So the knobs, which is the inputs to this test bench to generate constrained random sequences, are the following. There were 16 knobs for distribution of commands, 4 for each CPU, and the commands look like, broadcast read, broadcast write, read write, no op, and there's 12 knobs for controlling the address, 3 for each CPU. And like I mentioned, offset, index, and tag. So there's a total of 28 knobs that we wanted to find settings for. Now the output we captured from the test bench was the FIFO depth for each CPU at each cycle, and what we're measuring as the reward function is the average FIFO depth of all 4 CPUs. And our goal is to increase the average FIFO depth across all 4 CPUs. So the RL algorithm we used for test case 1 was, again, exactly like the DQN we modeled earlier. And the simulation setup looks like this, where we have the device under test running simulations. In this particular case, we used Verilator. And then from the results of the simulator, we essentially parse the rewards. In this case, the reward was the average FIFO depth. And that's fed into the RL agent. And the RL agent now produces the next knob settings of those 28 knobs that I just described for the next simulation, and so on. So the initial data set consisted of a set of random knobs and their average FIFO depths. And like I mentioned, this data set is fed into a DNN or an RL agent that learns a function that maps the knob settings to the FIFO depth. So in effect, it learns from the reward function, which is the average FIFO depth, to produce the next set of knobs. So the DNN, once trained, can be used to generate new knob settings and predict the average FIFO depth values. And again, once trained, the DNN essentially simulates the output for any new unseen knob settings, right? So this is the power of a deep neural network, where it can actually fit a function to even highly nonlinear behaviors. So the results of test case 1, which is maximizing the average FIFO depth, were really interesting. So the blue line, again, in this case, was just random choices of those 28 knobs. And the x-axis indicates a number of episodes. Each episode is one time step. You can think of it as one time step or one simulation. And the y-axis is the average FIFO depth. The FIFO depth goes from 0 to 15. So as you can see, the orange line is the reinforcement learning agent. And within 400 episodes, it starts producing average FIFO depths of 9 and above, which is a significant learning in 400 episodes. And then sort of continues to plateau out a little bit. So now you could say that, yeah, you could probably get high FIFO depths even with random and constrained random, but then you're leaving that to chance. What we were really trying to show here is, can a reinforcement learning agent learn enough to do better than random in a shorter amount of time? So this is the same data for the test case 1 results shown as histograms. So if we look at the first baseline simulation with random inputs, so this is no machine learning, just sort of random UVM generated knob settings. What this is showing you is the distribution of average FIFO depths, and the y-axis is showing you the occurrence. So you can see the distribution is average FIFO depths between 1 and 5, very few 5. And after one iteration of reinforcement learning, the distribution shifts significantly to the right, producing very high average FIFO depths. And after 2 iterations, you can see the distribution shifting even further to the right, which is what you want. So a lot of high FIFO depths, so almost 50, 45 occurrences of FIFO depths of about 10. So this is typically what we see with our reinforcement learning agent as applied to a hardware verification problem to optimize coverage, FIFO depth, and other signals that are hard to reach. So to run this cache controller, you can log into our website. It's free, and you'll be able to run this experiment live. So the test case number 2 was a RISC-V Aryan design, which has been renamed to CV-A6. So it's a 64-bit processor, and it looks like this. It has a 6-stage pipeline, in-order issue, out-of-order write-back, and we focus primarily on the data cache. And in the data cache, what we focused on is what's called the victim buffer. So the data cache is here in blue. So the data cache stores recently accessed data from memory. For all of you processor guys, you might know this already. And new cache allocations cause existing lines in the data cache to be evicted, right? Now, these modified evicted lines are held in what's called the victim buffer. So this is a very hard to hit condition where many things have to happen. There has to be collisions in address. There has to be collisions in the data cache for this to occur. So that's why we chose as our target to optimize the victim buffer count. So just a little about the design complexity of victim buffer. A cache line eviction and memory write-backs is complex, as I just mentioned. Victim buffer full requires back pressure for cache refills. That means there's got to be a lot of instructions backed up for victim buffers to get full. And why do you want to fill up a victim buffer? Because it uncovers other parts of the design that have not been exercised yet, perhaps. So the output we captured from this test bench is the average number of victims and the percentage of hitting max victim buffer count. And our goal was to increase the victim buffer count. So again, the simulation is set up exactly like the previous one, which is the FIFO test case, with the exception that in the FIFO test case, we had the 28 knobs that were set up directly with the test bench. In this particular case, what we were doing was we were using the Google instruction generator, and we were generating, or our RL agent is generating knob settings for the Google instruction generator. And the initial knob settings for the Google instruction generator are random. So the RL agent learns from each iteration as to which knobs impact the victim buffer occupancy. And then the RL agent subsequently produces knob settings for the next simulation run and feeds that into the Google instruction generator. And eventually it learns how to generate the settings which increases the victim buffer count, which is our reward function. So the list of knobs in this particular case were, there was a weighted wait for the load store jump branch instructions. There's a wait for other instructions. There's a wait for load, wait for stores, wait for jumps, wait for branches. And there's a tag and an index string. So these are the knobs settings that our RL agent was generating for the Google instruction generator. So the results again were pretty dramatic. The average victim buffer occupancy increased from 0.9 to about 1.6 in just 3 iterations. And again, a very similar picture. The blue line shows you random inputs to the Google instruction generator. And it shows you that the average victim buffer count never exceeds 0.9. And with the reinforcement learning agent that's generating knobs, very quickly, within 4 iterations, it starts to learn how to generate knob settings such that you get an average victim buffer count of 1.6 and above. So the maximum victim buffer count is 4. So essentially what the RL agent has done is identified the salient knobs and salient knob settings to the input to the Google instruction generator and exploits them. while exploring as well, as I mentioned earlier. So these are some of the results. Again, from case 2, this is iteration-wise average number of victims. And the x-axis is iteration, and average number of victim buffer count is on the y-axis. And you can see the RL agent starts producing much higher average number of victims than a random choice of inputs for the Google instruction generator. We also plotted the histogram of the average number of victims versus the occurrence. So the mean of the average number of victims is 0.95, and it increased pretty dramatically to 1.55 just in 4 iterations. The other metric, as we mentioned earlier, was we were also interested in recording the percentage of hitting max, which is how many times did you hit max victim buffer count, right? And the mean of that also significantly increased in 4 iterations, as shown in these 2 plots. So I want to talk a little about the future direction for ML for DV. We think reinforcement learning algorithms to handle large action spaces are required. This is an active area of research, and some very promising algorithms are what's called DDPG, Deep Deterministic Policy Gradient, and Soft Actor Critic, which is actually DDPG is based on Soft Actor Critic, but there's a particular algorithm called A3C, where it can handle large action spaces. And we're also exploring statistical algorithms such as contextual bandit and bandit algorithms. And in addition, in simulation RL or online RL. So what we showed you currently was sort of batched RL, where we take a bunch of simulations, learn from it, and produce a bunch of knobs for the next simulations. Online RL would be sim by sim, the RL agent learns. So we also feel RL will be deployed very widely to shorten debug and development time, automate bug finding, and reduce compute cycles used for verification. So in conclusion, we've demonstrated the value of using machine learning techniques on industrial design, such as the FIFO controller and the RISC-V 64-bit. And we've also demonstrated that it does significantly better than constrained random methods. Now, DNN provides a mechanism to fit any nonlinear function that can mimic extremely complex behaviors, perhaps even of a simulator. So using RL for DV, we believe can save months of verification resources for coverage improvement, early bug finding. And in addition, very importantly, can also dramatically reduce the energy used to verify a chip. So with that, I thank you for your time, and I'll open it up to any questions that you may have.
Thank you very much indeed, Sandeep. It was very, very interesting indeed. There are some questions, so let's go straight in. Can you see them? First one's from
yeah. Okay, Chris Edwards, are there risks in selecting metrics for RL machine learning models? The highly targeted ones, like FIFO buffer depth, may make sense. They explore a particular verification hypothesis. But more general targets, such as coverage, seem to present a danger of focusing on easy coverage that may leave difficult to reach states unexplored compared to more targeted goal rewards through coverage numbers wind up looking good. Is that fair? Wow, fantastic question. So I'll try to answer it as well as I can in the given amount of time. So like I mentioned earlier, there's a stage for exploration and exploitation. And if we're looking at just coverage, you mentioned easy coverage. But one of the things that you can also learn from coverage is the incremental coverage added by a particular test or a particular regression, right? So rather than using overall coverage as a metric, you could also choose to use incremental coverage as a metric, which can be more representative of doing exploration on the design. I hope that answers it. I'm happy to chat more. So this is from Sumedha Bengali. I'm sorry if I mispronounced the name. In both test cases, the RL learning output also plateaued after the first bump. Was it because it was already close to 100% of the reachability, or were they hard to hit waivable conditions? Yeah, a great question. So it does plateau, and as we simulate further, it does hit close to 100%. And we didn't waive any conditions on both these test cases. There were none to waive. Benedict Shemanek, do you compare results from ML also against constrained random testing done by VE traditional way? Yes, we did. And we're dramatically, significantly better. Or the RL agent is, rather.
Thank you very much for answering those questions. Are there any more from anybody? We're coming hard up against the end of the time slot. I will post a link in the chat. I would very much appreciate it if the three presenters could join in with the virtual environment. I suggest we congregate in the blue area, which is to the left as you enter. Well, you go up the stairs and then it's the room on the left-hand side of the main hall. I would really appreciate if everybody came in there, particularly if you have questions for the presenters. And it would be great to see that platform and to use that as a way of discussing what we've just heard. Just before we go, one last question from Christian Slav. If you would like to answer that, and then I would ask you all to come into the meeting, into the virtual room.
Okay, this is a good question from Christian. Christian says, how scalable is a technique for large number of coverage elements, not only for a large number of norms? In the real project, there are hundreds and thousands of coverage points to be hit. Can these be targeted all at once? So that's a great question. The answer is yes. And the answer is the following, which is you can either come up with a function that encapsulates all these coverage points by ANDing and ORing them together, if you will, in the most simplistic manner, or look at it as a distribution that can all be hit. Happy to chat about that more in detail.
Yep, absolutely. Well, let's, yeah, if everybody follows that link now and gets into the virtual room, let's continue those discussions because they were really, really good. Thank you very much indeed, Sandeep, and thank you to all three presenters. We're exactly at the top of the hour. Yes, please, everybody, jump on that link and see you in 2 minutes.
Thank you.
Thanks, and bye.